assessment tells us that this starting material gives the same product, whether treated under cold or warm conditions. Why is that, and what is the product? Well, let's start by going through the mechanism. If we start with our alkene attacking HBr, kicking out Br- as a leaving group, we will form a carbocation intermediate. This step is the same regardless of the temperature at which the reaction is run. This intermediate can be stabilized by resonance. That's where we get the 1,2 versus 1,4 addition product. And from here, we can think about what products we can form at cold temperatures and elevated temperatures, and which one is going to be our product for this reaction. At cold temperatures, we're under kinetic control, and so the molecule will, or the product will form, that is the fastest product that can form. And that product is when the Br- attacks the carbocation directly adjacent to the hydrogen to which it used to be attached. That is going to form the product with the bromine next to the hydrogen from HBr. This would be the kinetic product under cold conditions. Under thermodynamic conditions, we typically use the other resonance contributor, but let's really understand what we mean by thermodynamic control. The thermodynamic product is the most stable product, regardless of what that product is. If we look at these two carbocation intermediates, the thermodynamic product will be the product that gives us the most stable alkene possible. If we use this first carbocation, then we would end up with a tri-substituted alkene. And if we go through the second carbocation intermediate, we would end up with a di-substituted carbocation, or a di-substituted alkene product. A tri-substituted alkene is more stable than a di-substituted alkene, so the thermodynamic product will form the product that gives us the most stable alkene, which is also the tri-substituted alkene product. So both kinetic and thermodynamic control give us the same product from this starting material.